So chapter 3, we are dealing with gravitation. We're dealing with gravity, the pull between different bodies. And what is this? Well, let's see. What is this? So some important questions that we need to answer in this chapter. What are Newton's universal law of gravitation and Kepler's laws? So there are different laws and different formulas that we're going to study, and we're going to understand what it is. And so the main thing that we want to take away from this chapter is, what is this law? How do we use this law? How does this law affect us? And how can we use this law? How do we apply it in our daily lives? The second question is, why is it important to know the gravitational acceleration of planets in the solar system? So we know what is the gravitational acceleration of Earth. We've studied that before. It's an average of 9.81 meters per second. Okay, that's useful for us because we live on Earth. But what about the gravitational acceleration of other planets? What's the use of me knowing what's the gravitational acceleration of Mars, of Jupiter, or of Neptune? Planets that are so far away, especially Uranus and other planets, that it's not likely that we'll visit those planets anytime soon. So then, if that's the case, then why is it so important for us to understand and be aware of the values of this gravitational acceleration? How can we use that? How does that help us? Or how does that help us to learn new things? Okay, the third thing is, how do man-made satellites help improve human life? So focus on the word man-made. If they are man-made satellite, that means they're also natural satellites, which are not made by man. But we're focusing on man-made satellites, and how do these satellites help to improve our human life? So these are the three things that we are going to discuss and try to find out in chapter 3. So these are the three topics, basically. 3.1 will be talking about Newton's universal law of gravitation. Second one, 3.2 will be Kepler's laws. And the third we'll be talking about man-made satellites. How do we use them? What do they do? And how do we install a man-made satellite? All right, so famous story. Isaac Newton. The story goes, Isaac Newton was sitting under a tree. And while he was sitting under a tree, an apple fell on his head. And after the apple fell on his head, he started to think, why do things fall down? Why do things fall down? It's such a simple question. And a lot of things in science start with these seemingly simple questions. But it's when we explore these simple questions that we start to learn a lot of interesting things. So in 1667, the scientist Isaac Newton, what he did was he observed two things. He studied two things. The first was an apple which fell vertically to the ground. He studied how things would fall to the ground. The second thing was that he studied the movement of the moon around the earth. He thinks, why does the moon go around the earth? And so his conclusion was that there is a force of attraction. So there is something between the earth and the apple that pulls these two things together. That's what they call attraction. And he also made the same assumption or conclusion about the earth and the moon. There has to be something between the earth and the moon that is pulling these two things together. There is an attraction. So this is how he came up with the universal law of gravitation. It's very interesting. Even before they had all the modern equipment that we have today, they were able to come up with this idea or with this law of gravitation. They were able to study these things. So gravitational force is known as a universal force because it acts between any two bodies in the universe. So anytime there are two bodies, whether it's a planet and another planet, or a planet and a moon, or a planet and a star, or anything, whether it's two small objects or two large objects, there is a gravitational force wherever you go in the new universe. So whenever we have two objects or two bodies, there is gravitation, there is pull, there is attraction between these two things. And so the reason why this is so important is because this is something that happens throughout the entire universe, not just on Earth. And so to understand gravity, to understand gravitational force, will bring us one step closer to understanding the universe. It's a basic force in the universe. Gravity explains why planets go around the sun. It explains why why stars are so powerful. It explains why stars are able to create energy. It explains why stars, what happens when a star runs out of fuel, what happens when a star dies. It just explains so many things that to understand gravity is to understand is it does. I mean, it's not. We won't understand everything in the universe just because we understand gravity. Of course not, but it takes us a step closer. And so gravity as a whole is very important in the field of physics, especially in the study of space and in the study of theoretical physics. So in the year 1687, Isaac Newton presented two relationships that involved gravitational force between two bodies. So he came up with two relationships. This word relationship in physics is very important. And so I want to talk about that a little bit more. First one is gravitational force is directly proportional to the product of the masses of the two bodies. That is, F or force is proportional to the product of the two masses of the two bodies. So if we were to draw this as a picture. So if we were to draw a picture of this. So if we were to imagine there were two bodies or two planets. And let's say let's find a better marker. So let's say there's planet 1. And planet number 1 has its mass. And so let's call that mass 1. And let's say there's planet 2. And this also has its mass. So Newton's law of gravitation, the first relationship that he comes up is this. F is proportional to m1 times m2, or the product. Let me just draw that better. Now, when I talk about the word relationship, all right? So, in normal day-to-day speaking, a relationship means that what kind of you might say what kind of relationship you have with another person, right? You may have a relationship as friends, or maybe you have no relationship, then you call them strangers. But when two people, I'm using this analogy, when two people have a close relationship, and maybe they are brother and sister or husband and wife or family. When two people have a close relationship, what happens? They tend to share things together. If something happens to one person in this relationship, it also tends to affect the other person in the relationship. For example, if two people love each other very much, if one person in the relationship becomes very sad because of something that happened to them, something bad happens to them, it also affects the other person in that relationship. The other person might also share in their sadness. That's what we call, human relationship. What affects one in the relationship also affects the other. In physics, we have the same idea. When we talk about the relationship of two things or the relationship of two values, what it's talking about is how does one value affect the other. If I change one side of the relationship, what happens to the other side? So for example, we have this. Gravitational force is directly proportional. So the word proportional gives us or tells us the meaning of this relationship. The word proportional means if one side of the relationship increases, then the other side will also increase. That's what it means. So if we take a look at this formula here, if we increase the mass, the mass of any of this planet or any of these bodies, what happens to the gravitational force? Simple mathematics. This is a product, so if any of these numbers increase or go higher, simple mathematics tells us that this will also get higher. So by logic logically speaking, if we were to take two planets or different planets, let's say we have these two planets and we compare it with another two planets, but the other two planets are much smaller. Now, based on the formula that we just learned, that F is proportional to mass 1 times mass 2, based on this formula, the gravity, let's call this force 1 and let's call this force 2, right? Based on this formula, which one is bigger, F1 or F2? Just logically speaking. Okay, so logically speaking, right? Thank you, Johan. So logically speaking, since these two have larger mass, it also follows that the force between these two is also larger. So we can say F1 is larger than F2 because that is what the law says. This is how we take a formula and start to think about what this formula means. This is the important part of physics. It's not enough to just memorize the formula, but we have to think about what does this formula mean. Now, on the other side, let's say we do not know how big the different planets are. Right? We don't know how big the planets are. We only know what is the gravity, or we can see the effects of the gravity. Let's say you're a scientist, you haven't seen this planet yet, or this planet is very far away, and so you can't really tell how big it is. But you can see the gravity, you can see the effects of the gravity, and then you can tell that, for example, that this one, the second set of planets, has a bigger gravitational force than this one. So in this case, F1 is bigger than F2. In that case, between set number 1 and set number 2, which one is more likely to have bigger planets? Or which one is more likely to have the bigger planet? Logically speaking, the one that has more force, or the one that has a strong gravitational pull, it's most likely that at least one of these planets will be bigger compared to one of these planets. Again, this is just based on the formula that we have just read. And so this is how scientists can take a formula and study things that even though they're not able to see it completely, they can at least make some guesses. They can tell, okay, this planet seems to have a strong gravitational pull. That means it must be quite big. Or this planet seems to not have a very strong gravitational pull. So maybe it's not that big of a planet compared to other planets. Okay? If you have any questions, just go ahead and type in the chat. So that is the first relationship. The relationship between the gravitational force and the mass, the product of the mass of the two bodies. The second relationship is also very important. The gravitational force is inversely proportional. So inversely means the opposite. Inversely proportional means when one goes up, the other goes down. That's what inversely proportional means. Proportional means when one goes up, the other goes up. Inversely proportional means when one goes up, the other goes down or decreases. So the second relationship is the force, gravitational force, F, is inversely proportional to the square of the distance between the two bodies. That is, F is inversely proportional to 1 over r square. So once again, if we go to a whiteboard, let's say we have 2 planets. Right? Now, when we measure the distance between 2 planets, we measure from the center. I keep on saying planet, but it's not necessarily a planet, by the way, even though I keep on saying planet. It can also be any other large object in space. Asteroids, stars, even black holes. Okay? And it can be any other thing. So, anyway, where was I? So, F is proportional to 1 over r square, r being the distance between the 2 planets. Now, when we, where was it? When we measure from center to center. So, not from here to here. That's wrong. All right? Because you're only measuring up to the surface. You need to measure all the way to the center to get an accurate reading. So you have to measure from here all the way to here. This is the value of r. So, once again, just thinking logically using the formula that we already know, let's make a comparison. So if we had 2 planets, 2 sets of planets, now this time both planets are of the same size, but we know that the formula is, we know that force is proportional to 1 over r square, meaning to say the longer the distance, the lower the gravitational force. So, if we were to have 2 planets, same mass, this time the mass, assume that this planet, even though it looks different, assume that these 2 planets are of a different, are of the same mass as the first 2. But the distance between these 2 is greater. So this is R1 and R2. Then we can make the assumption that which one will have a stronger gravitational force? F1 or F2? The one that's closer or the one that's nearer? I think I just told you. So obviously just based on this formula, we can tell that whichever is closer has a stronger gravitational force. That is what this formula is telling us. At the same time, we also know that we can also use this to try and guess which 2 planets are further away. So let's say we have the Earth. Let's call this E, Earth. We have planet A. We don't know how far planet A is because our telescope is not good enough. And we have planet B. And after studying for a while, we find that planet F has this gravitational pull of, let's say, has this gravitational pull of a certain amount, and planet B has a gravitational pull of a certain amount, and we know that planet A and planet B are of the same mass, right? We just assume that they are of similar mass, but we don't know which one is further away. But if we know that, for example, the force from planet B is larger than the force from planet 1, then based on the formula that we were just looking at just now, that the force is directly inversely proportional to the distance, then we know that in all likelihood, the one that has the stronger force is also likely to be closer. So therefore, R1 is probably further away. So R is larger than R2. Right? These are just ways for us to think about these different formulas. And so the reason why I want to take time to talk to you about this is because, a lot of times we just learn the formula and we learn how to use it. And maybe it's also my fault because I don't tell you anything else. But we also want to think, what does this formula mean? How does this, if I approach this formula from different angles, how do I interpret this formula? How do I apply this formula? That is how you understand. This is how you use, and this is how you're going to pass physics. Basically, it's not just by memorizing the formula. And remember, a lot of the formulas are given anyway. At least it used to be. I hope for you guys it'll also give you the formula, right? Okay, so now that we've talked about the relationship between, now that we've talked about the relationship between these two, these two things, these two relationships that we have, now we can go to Newton's universal law of gravitation. So if we were to combine everything that we learn, if Newton combines everything, we get this formula. So Newton's law of gravitation states that the gravitational force between two bodies is directly proportional to the product of the mass of the two bodies, yes, and inversely proportional to the square of the distance between the centers of the two bodies. So if we were to write this down as a formula, let me unblock it. This is the formula that you would end up with. Force equals G m1 m2 over r square. Force meaning the gravitational force. Okay, inversely. So I'll repeat again. So inversely means it's basically an easy way of saying. So usually when we say something has an inverse relationship or inversely proportional, it means that when one goes up, the other goes down. That's their relationship. So kalau macam manusia, maybe it's like two people that hate each other. If one is happy, then it makes the other person sad because he's happy. Kind of opposite. Let me try to think of an example of inversely. I mean, if you write it down in an equation, usually an inverse equation looks something like this. It can be anything, right? A equals 1 over B. So the higher B is, so if A equals 1 over B, the higher B is, the lower A becomes. Because, for example, if B equals, let me just write it down. If B equals 1, then A equals 1 divided by 1 equals 1, right? But if B equals 2, so this time B is getting bigger, A gets smaller, A becomes 1 over 2, and so on and so forth. So the larger B becomes, the smaller A gets. That's what we mean inversely proportional. The larger one number gets, the larger this number gets, the smaller. So the larger A is, the smaller B is. The bigger B is, the smaller A is. That's inversely proportional. The opposite of inversely proportional is directly proportional. So directly proportional is the opposite. So directly proportional is something like A equals B, C. Let's say C is constant, so C doesn't change, right? So if A equals BC, actually, let's do it like this. A equals 2B. That makes it easier for us. Let's say this is the relationship. They are directly proportional. So if B equals 1, A equals 2. If B equals 2, then A equals 4, and so on and so forth. When B gets bigger and bigger and bigger, A also becomes bigger and bigger. So they sort of grow together. But inversely is the opposite. When one gets bigger, the other becomes smaller. That is what inversely proportional means. Okay? Faham sudah? Hopefully that answers your question. Oh, Yeah, so that's what I was saying. It's kind of like two people that hate each other. You know, when two people hate each other, when one person is happy, the other person becomes sad because they don't like the other person being happy. Right? But don't be that person. Okay, back to the equation that we are talking about. So Newton's universal law of gravitation can be expressed as follows: force equals G m1 m2 over r square. So gravitational force is the force of the gravity between two bodies. M is the mass of the first body, so you need to know the mass of the first body or first planet or first object. M2 equals mass of the second body or second object. R is the distance between the center of the first body and the center of the second body. And G equals gravitational constant. So gravitational constant is a number that scientists have agreed that this is constant throughout the entire universe. Right? So we use this number when we are trying to calculate the gravity of anything. And so gravitational constant is G equals capital letter G, yeah? Not small letter g. Small letter g is 9.81 gravitational acceleration of the Earth. G, capital letter G, is gravitational constant. So gravitational constant is defined as 6.67 times 10 by the power of minus 11 newtons per square meter per kilograms raised by negative 2. Alright, so that's the formula. We'll go through this formula later and we'll do a few examples as well. Now, another important thing for you to understand. This is the formula, but this is not the definition. This is the definition. If in SPM or any exam paper, and this is also something that they was shared during the seminar. If the question asks you, what is Newton's universal law of gravitation, or state the meaning of Newton's universal law of gravitation, you cannot just simply write down the formula. Now, I've also made this mistake in the past. In the past, I would accept if you just wrote down the formula. So for example, sometimes when I ask what is force, what is force, then you write force F equals ma, mass times acceleration, ma. You cannot write that down. You cannot write that down as your answer. You have to write it down in a sentence. You have to write down force is the product of the mass of an object and its acceleration. Right? You have to answer like that. So when you are answering in SPM physics later, you have to state this. Not necessarily exactly word for word. It doesn't have to be exactly word for word, but you have to have all the keywords. So you need to write down gravitational force between two bodies or two objects, directly proportional to the mass of the two bodies and inversely proportional to the square of the distance between the center of the two different bodies. So you have to have, it has to be simple. You have to have all the keywords. That is when you're giving a definition. But if you're going to give the formula, then you can, or if the question says express Newton's universal law of gravitation as a formula, then you can write down this formula. Okay, so the easiest way for us to understand is for us to try a few questions. So, but let's take a look at this formula first before we continue to the questions. So just like what I said just now, G is constant. That's not going to change. So the only thing that you can change is the mass of either planets and the distance. So how can we increase, for example, how can we increase the amount of force? We could increase the mass of the planets, for example. If one of the mass is bigger, then you'll get up with a larger force because m times a larger number will end up with an even bigger number. But the second one, r square, if you increase the value of r, then you'll actually divide this more. So you'll end up with a smaller force. So that's how we combine the two relationships that we talked about just now. Okay, let's try a couple of examples. So yes, if you know the masses of two bodies and the distance between the centers of the two bodies, you can calculate the magnitude of the gravitational force between the two bodies. So these are the two things that you need to know: the masses and the distance. These are the two things, so these are the important pieces of information in every question when it comes to Newton's universal law of gravitation. All right. Now, go ahead. You can check your textbook because this example is in your textbook, right? So actually, you don't have to write down my example if you don't want to because it's in your textbook. But I'm going to go through it. So calculate the gravitational force between a durian and the Earth. So you might think, can such a small object like a durian have gravitational force? The answer is yes. Even between a small object like a durian and a big object like the Earth, there is actually a gravitational force between these two objects. You're sitting on a chair or lying down at home or sitting at a table watching your cell phone or a desk. You also have a gravitational force between you and the Earth. It's not just the Earth that's pulling you; you are also pulling the Earth. That's actually something that's actually quite interesting to think about. So which one is M1 or M2? Can it be any? Yeah. So we'll go ahead and try it. We're gonna go ahead and solve it right now. So the distance of the center of so where was I? Yes. So distance between the center of the durian and the center of the Earth is already stated to be 6.37 times 10 by the power of 6. So they've already given us all the different things that we need. So let's go ahead and figure that out. So the formula is force equals G, capital letter G, times M1 times M2 over R square. So let's figure out the value of each of these things first. So what is G? So G we've just discussed just now. G is constant. So some questions might not give you G. So make sure you remember this. So G equals 6.67 times 10 by the power of negative 11 Newton per square meter kilogram raised by the power of negative 2. So this is the value of G. So that is never going to change. Whatever question you see, value of G is going to be the same. Okay, let's put the durian as M1. It doesn't really matter because you can put either one and you'll still get the same result. But let's use the durian as M1, mass 1. So durian is 2 kilograms as per the question just now. Now the mass of the Earth, let's use it as M2. Mass of the Earth equals 5.97 times 10 to the power of 24 kilograms. And finally, at the very end, so the distance between the center of the Earth and the center of the durian, which is R. So R equals 6.37 times 10 to the power of 6. Now, in this chapter, you notice that we tend to be dealing with very, very large numbers. That's because gravity tends to involve big things such as planets, and it also tends to involve big distances. So, for example, between the planet and the sun, or the planet and the moon, or any other large distances. So, we tend to have a lot of big numbers in this chapter. Okay, so let's just put all of these values into the formula that we have already studied. So, I'm running out of space, so let me just rewrite it there. So we're gonna find out force. Alright, so G we already determined is 6.67 times 10 power of 11. And go ahead and take out your calculators now to help me with this. All right, and then times mass 1, which is 2, times mass 2 equals 5.97 times 10 by the power of 24 over 6.37 times 10 power of 6 square. Okay, so based on your textbook or based on your calculators, what is your final answer? It's a bit too big for me to calculate off the top of my head. Can someone share the answer? Or can someone try to check on a calculator? It's what is this? Times 2 times 5.97 power of times 10 by the power of 10 power of 24. Yeah, okay, go ahead. I'm also calculating. Actually, it's in the textbook, but go ahead and calculate that. Divided by 6.37 times 10 power of 6 square. So my calculator tells me that it is, if I wrote down the full answer, it would be, wait, that can be correct. Oh yeah, that is correct. 1 9 6.2 6 8 8 1 3 0 4 4 blah, blah, blah. If we were to round it off to 2 decimal points, it would be 196.27. Is that correct, or did anyone get a different answer? It's possible I got it wrong. It is in the textbook, by the way. Yeah, okay, so the buku text is 19.63. Okay. What that means is that I made a mistake with one of the tens. Okay, so there was a mistake there. Okay. So the decimal point is here. So 6 3. Sa silap, I probably miscalculated one of the tens tadi. Okay. 6 3. Okay. So 19.63 and newtons. So that is your final answer. Okay, now think about this. Okay, now that you've seen me write this down, think about this. Think about this logically. Okay, both the durian, or actually, the first question is, the gravitational force is 19.63. The question is, which body, because we have two bodies here, we have the durian and the earth. Which body is experiencing 19.63 newtons? That's the first question. Which one do you think it is? Is it the durian or is it the earth that is being pulled with 19.63 newtons? What do you think? Is it the durian or is it the earth? Keman says durian. How about the rest of you? Is it the durian that's being pulled by 19.63 newtons? Or is it the earth that's being pulled by 19.63 newtons? Now, logically speaking, it's logical for us to think, the durian is the one that's moving, so it's the durian that's being pulled towards the Earth. So it's the durian that's experiencing 19.63. But let me ask you a question. How do you know it's the durian that's going to the Earth and not the Earth going to the durian? Maybe the durian is staying still and it's the Earth that's moving up to the durian, but it just looks like it's falling to us. Maybe it looks like the durian is falling, but it's actually us that's staying still, and the durian. No, it's actually the durian that's staying still, and it's the Earth that's moving to the durian. How do you know that? Okay, this is how you know. So actually, that's a trick question. It's kind of a trick question because. Okay, okay. Some of you are a little surprised. Okay. It's fun to ask questions like that. Okay, let me show you how this is. The answer is both. Gravity works, or I should say gravitational force. Gravitational force works on both bodies. Both the Earth and the durian is experiencing 19.63 newtons. At least according to the question that we just did. Both of it is experiencing the same amount of force. Now, if both the Earth is experiencing the same amount of force, meaning to say, in theory, both the Earth and the durian are moving towards each other. They are both actually accelerating towards each other. But, this is the important thing. But, remember, acceleration equals what? Equals force divided by mass. Right? Because force equals mass times acceleration. So acceleration equals force divided by mass. So let's say that force is already calculated just now. Force is 19.63. So let's see. What is the acceleration of the apple, for example? So the apple is 2 kilograms. So the acceleration is 19.63 divided by 2. And what do you get? 19.63 divided by 2, what's the answer? Is it 9.81? 9.8, yeah, so 9.81 or 9.82. Okay, 9.85. So very close to what we know is the acceleration of gravity. So it's accelerating at 9 meters per second. So quite fast. Now, let's compare with the acceleration of the Earth. How much is the Earth accelerating compared to the apple? So same force, 19.63. But what is the mass of the Earth that we just saw just now? Let's look back. The mass of the Earth is much bigger. It's 5.97 times 10 power of 24. So the acceleration for the Earth, so let's call this acceleration 1, acceleration 2. So the acceleration for the Earth is different, 19.63 over 5.7 times 10 power of 24. So what is the answer there? So how much is the Earth accelerating? Probably not a lot. So it's, what is this? 19.63 divided by 5.97 times 10 to the power of, 10 to the power of 24. So I am getting, according to my calculations, 3.3, I rounded off, 3 point blah 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 blah, times 10 to the power of minus 24. Did everyone else get that answer? It's not going to be 3.3. It's 3.3 times 10 to the, It's not 3.3. It's 3.3 times, yes, 3.3 times 10 minus, yeah, it's minus. Yes, times minus 24. In other words, if we were to write out the full number, standard form, if we were to try to write out the full number, so 3.3 plus or minus 24, we have to move the decimal point. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So each of these steps, there's a 0. So I don't even have enough space to write down all the zeros. So basically, it's 0.00033. In other words, it's a very, very small amount, very, very tiny acceleration. So it might as well be that the Earth is not moving. But in terms of physics, the Earth is actually being pulled towards the durian at the same time the durian is being pulled to the Earth. But because the Earth is just so much bigger than the durian, the fact of the matter is it's almost as if the Earth did not move at all. Alright? So it's an interesting way to think about it. It's very interesting. It's an interesting way to think about it. It's like, positive thinking. The Earth is pulling me, but I'm also pulling the Earth. Some people like to say, when I do push-ups, I'm not pushing myself up, I'm pushing the Earth away from me. It's just a different way of seeing things. This is why physics is so interesting. Sometimes it gives us a different way to see things. So, back to my original question. Is it the Earth or is it the durian that's moving to each other? It's actually both. But because the Earth is just so much bigger, even though they're experiencing the same amount of force, the Earth just barely moves. No, the force is not different. The force is the same. It's the acceleration or the speed. The force is the same. Both are experiencing 19.63 newtons. The force is the same. It's the acceleration that's different. Remember, because acceleration is a product of you get the acceleration by dividing force with the mass. So yes, interesting thing to think about. Okay, same force, same different mass and different acceleration. Okay, very good. So I hope you understand that. So if the question asks which one is experiencing 19.63 newtons, it's both. Okay, question number 2, example number 2. Okay, a rocket at a launching pad experiences a gravitational force of 4.98 times 10 to the power of 5. What is the mass of the rocket? Okay, so mass of the Earth has been stated. Distance between the center of the Earth and the center of the rocket is also stated. And the force is also stated this time. So this time we have the force, but what we're looking for is the mass of the rocket. So let's use the formula again. So let's write out the formula. So F equals G M1 M2 over R square. Right? So what is force? Force is already given to us. So force is stated to be 4.98 times 10 power of 5. So that's a lot. That's a big number. And then, mass of the Earth. So let's make Earth M1 this time. So mass of the Earth is 5.97 times 10 to the power of 24. And the distance is also given. So the distance is given as, the distance is given as 6. So R equals 6.37 times 10 to the power of 6. So this is the information that we have. And what we need to figure out now is how much is M2. Not stated at all. So berapa lah tu? So let's try find it out. So let's put everything in the formula. So force equals gm1 m2 r squared. So force, this is pretty long. So I might have to use the other side. Oops. So I'm gonna go ahead and use the other side because it's pretty long. Not a long question, but just the the writing down. Yes, pindah the formula. So let's write down everything first. So 6.37 times 10 power of 6 equals G. What is G? Again, G is not given, but we know how much is G. G is 6.667 times 10 minus 11. All right. And then M1 also we already know mass of the earth is 5.97 times 10 power of 24 times M2. I'm running out of space, but it's in your textbook anyway. You should be able to see it. Okay, over distance between center of the earth and center of the rocket is 6.37 times 10 power of 6 square. All right, so susun. How much is the value of M2? Please go ahead and calculate that. What is the mass of the rocket? I'll give you a few minutes to figure that out. I'm sorry, I made a mistake. The force is not 6.37. The force is, I read the question wrong. The force is 4.98. Yeah, okay, that's the correct force. Okay, sorry for that. All right, go ahead and calculate that. So if we were to rewrite the formula, we move this there and move this down there, and we end up with, it's a big, it's a big calculation. Okay, make sure to not forget all the power of tens and whatnot. There's a lot. Okay, so anyone calculated or did anyone read the textbook for the answer? Calculating. Yeah, so it can get kind of long. You may have to do it step by step since it's such large numbers. So you may prefer to do it step by step. Excuse me. The force. There. The gravitational force. Oh, sorry, wrong question. All right, there you go. That's the gravitational force. Yeah, sometimes with bigger numbers, it takes a little bit of time for us to write everything out. Like I said, there is big numbers for this chapter. So yeah, for this chapter, expect to be dealing with fairly large numbers. Kamu kena biasakan dirilah dengan standard form because for big numbers memang dia akan banyak menggunakan standard form. So kalau kamu belum biasa guna standard form, then I would suggest that you start practicing standard form immediately. Kamu review that chapter. Okay, anyone has an answer to share? I already have the answer, or you can just write. You can just show the answer from the textbook. But if you want to calculate it out, that's also good. Here's a hint while you're working on that. Here's a hint. Go ahead and try and remember how index numbers work. How index numbers work, because that's really helpful when using standard form. If you can remember how to use index numbers and things like what's this, indices. If you can remember how to use those, it'll really help you when you're doing a question with standard form, big numbers. Okay, I'm gonna go ahead and show the answer. So once you finish rearranging everything, you finally end up with your mass of your rocket being 5.07 times 10 to the power of 4. Yes, right, 10 to the power of 4. Or 5. Actually, you can just write it as 50,700. That would be the full form. But, standard form, so 5.07 times 10 to the power of 4. Usually you round it off to a few different, to a few places. Okay, so that's how you use the formula or the law of gravitation. All right, so let me just touch on one more thing, and then we'll be finished for today. I think we're almost out of time, and I don't want to give too much anyway. All right, so last thing that we're gonna talk about. Relating gravitational acceleration g on the surface of the Earth with universal gravitational constant g. So we have learned already what is gravitational acceleration. We know how much is it. We know how it's roughly 9.81. And if you want to go on and on, it might be a little bit high or a little bit low, but basically we standardize it as 9.81 meters per second on the surface of the Earth. Gravitational acceleration, we symbolize it with small letter g. What is the relationship between gravitational acceleration g and universal gravitational constant capital letter G. What is the relationship? Is there a relationship between these two? Does one affect the other? Basically. So we are going to do it. So there's a very easy way for us to show the relationship is by using the formula for these two different between these two different numbers or these two different values. So according to Newton's second law of motion, gravitational force can be expressed as force equals mass times gravity or gravitational acceleration. We learned about that. That's how you get the weight of an object, the force of its weight. Now, we also just learned today that Newton's universal law of gravitation, gravitational force, is expressed as F equals G, capital letter G, M1 times M2 divided by R2. So these two things we can relate to each other like this. So we're going to use mathematics or very simple mathematics. This isn't hard mathematics. Okay, so let's write down both formulas first. So F equals mg. At the same time, we also know that F equals g m1 m2 over g. Can we use substitution maybe? So let's use substitution because F is equal on both sides. If F equals mg and F equals g m1 m2 over g. Sorry, not g, r square. I wrote down the wrong formula. Right, these are the two formulas that we just learned. If this is correct, then mg must equal capital G m1 m2 over r square. So let's write that down. mg equals gravitational constant, letter G, m1 m2 over r square. Now m, since this is two forces, they both have the same m. So m1 mg equals this. Okay, now can we simplify it? Yes, we can. Since they both have an m here, we can cancel this out. So we can simplify it as the relationship is gravity equals gravitational constant, capital letter G, equals times mass times r square. So this is how we can calculate the gravitational constant. So if we were to try find out what's the gravitational, this is how we found out the gravitational acceleration of the Earth. Okay, we found out what is the gravitational constant, and we know what is the gravitational force of the Earth, and we know the distance from an object to the center of the Earth, and we get around 9.81 or so. So that's the relationship between these two. All right, we'll go into this more next week. I think that's enough for today. If I give you too much, then it's also not good. If I give you too little, it's also not good. Gravitational constant is fixed. Yes, that's correct. Gravitational constant is, like we looked earlier, is always going to be 6.67 times 10 by the power of negative 11 Newton per square meter by kilograms raised to the power of negative 2. So yes, gravitational constant is fixed. That's why it's called constant. It's constant. It doesn't change. So no matter which planet you're calculating or what space body you're trying to calculate, you're always using the same gravitational constant. That is why in this question, in other questions like example 2 and example 1, they did not give the gravitational constant because it's always going to be the same. So this is a number that you need to remember. You need to memorize this number. All right. So that is the relationship between G and D. Right, we just did that. All right, this is for next lesson, variations in the value of G and R. We'll learn that next week because next week chuti. All right, okay. So any questions before I let you do your assignments? Okay, do you have any questions that you would like to ask? Any maybe something about the formula that you're not so sure about, or something about space in general, or about what about how gravity affects us in general? Any questions you'd like to ask? What if? What if? Actually, what if is a very good kind of question for science. Actually, a lot of questions in science, a lot of discoveries in science start with what if. Okay, so if you don't have any questions, or you can ask it later if you want. So for your assignment today, please go ahead and do activity 3.3 in your textbook. You'll be able to calculate and answer all those questions. It's quite simple. I mean, it's straightforward. It's just basically applying what we just learned just now. So go ahead and do activity 3.3 in your textbook, and later pass it in. I'll send you a link for you to upload your assignment, so that it'll be a little bit easier for me. Okay, so yeah, that's your assignment for today. So you know what to do. I will send you the notes for this class later, and I will be uploading this class onto YouTube as well for you to review. Okay, so if you don't have any other questions, then you are dismissed. Thank you very much for listening. Have a nice day. Okay, goodbye, goodbye. Thank you, thank you, thank you. Okay, you're welcome. Okay, that went very well.